Hello guys, nice to see you. So we continue our discussion of two-dimensional motion in two-dimensional case. And first we recall shortly what we discussed during our lecture. So we introduced the vector form in two-dimensional system of coordinates, vectors of velocity, instantaneous velocity, and instantaneous acceleration. Based on that, we could already derive the kinematic equation in vector form, which can be applied to either two or also can be extrapolated towards three-dimensional case. So by using instead of only I and j unit vectors, also we can go for k unit vectors and represent axis z if necessary. So with that in mind, when we had already time dependence of position vector, which gives us the kinematic equation, we could describe some example, like quantify some example of two-dimensional motion with uniform acceleration, and that was a projectile motion, which we discussed during the last lecture and derived certain equation which describe the features of this two-dimensional motion with constant acceleration. Today we continue this topic of motion in two dimensions and we'll consider one very important example of two-dimensional motion, namely uniform circular motion. So uniform circular motion that used like building block of different types of motions. So we definitely want to understand what's going on there. And today we're going to first introduce this main concept of and parameters of uniform circular motion. Then we would like to quantify the so-called centripetal acceleration with a simple approach, straightforward, with some graphical representation, which gives us both magnitude and orientation of this acceleration vector. And also after that would be good to discuss also a detailed analytical solution for deriving this centripetal acceleration vector as a function of time. So we can clearly see that both approaches, which are quite different from each other, but lead us to the same result. Okay, so let us first consider general things about uniform circular motion. We obviously need to have some circular trajectory. And let us pick up 2 points here. That will be point A, point B. Initial and final point of this body motion along circular trajectory. You're welcome. So here is the center of this curvature. And we can now introduce position vectors like initial position vector and final position vector. Since the magnitude of position vector doesn't change because it's a circular trajectory, it also can be called as radius vector, which defines the position of the body on a circular trajectory. We also need to introduce linear velocity vectors. So this is initial linear velocity vector, and this is final velocity vector. We mentioned at the beginning that this is not just circular motion, it's uniform circular motion. What does it mean? It means that the magnitude of linear velocity vector remains constant. it doesn't change. So in this case, if magnitude doesn't change, any suggestions? Do we have some acceleration here?
No. No.
But we do. Yeah, it could be counterintuitive because on one side, uh, I see your logic. So we have definition of acceleration as the first derivative of linear vector uh, over time, and linear velocity, like vector over time. If magnitude doesn't change, so could be that it's equal to zero, and we don't have any acceleration. However, we deal with a vector quantity, not scalar, and we have not only magnitude but also orientation, so it's a vector. And you can see here that the orientation of velocity vector is changing. Keep in mind that we always have right angle between radius vector and velocity vector. So it's always perpendicular to each other. So if we change our radius vector towards a new position, position of linear velocity vector will also change. So there is uh, some consequence of change of orientation of linear vector, velocity vector, and that consequence is so-called centripetal acceleration, which is oriented inwards of the curvature towards the center. So goes like this. Let us show with a different color. At every moment of time, because of change of orientation of the velocity vector, we have such a acceleration vector, which is called centripetal acceleration vector, and this vector is always perpendicular to the velocity vector. It's aligned, so it's parallel to radius vector, but aligned in, like, pointed in opposite direction. So we always have position vector pointed from the curvature towards the position of the body. And in the case of centripetal acceleration vector, it's pointed in the opposite direction toward the center of the curvature. The same will be here. We have this centripetal acceleration vector. So that is happening because of change of orientation of velocity vector. So that's the only reason for having this centripetal acceleration. So now let us define a difference between so-called centripetal and centrifugal forces, so which are associated with respective accelerations. Because obviously, if we have acceleration, we have some force acting on the mass, so we will in details discuss it in quite soon. But in order to avoid possible misunderstanding for the future, let us introduce this difference now. So uniform circular motion, so I pick up some old webcam, hope it will not detach, looks pretty much like this. And the key moment here that the linear velocity vector of this webcam should be constant. So what is happening here? Because of the fact that this wire does not allow this webcam to move straight along a straight line, it always exerts some force to keep it going along this circular trajectory. So always at every moment of time there is some force exerted from the side of the wire on the webcam to keep it on the circular trajectory. So that is so-called centripetal force associated with centripetal acceleration, and it's pointed from webcam towards the center of this curved trajectory on this circle. So from other side, we can, if we consider, so that's what you observer considers when it's attached to system of reference outside this wire and webcam. However, if we consider this webcam with being attached with system of reference to the webcam, then there will be some apparent force which kind of tries to push this webcam away from the center, and that is so-called centrifugal force. So technically, these are kind of different sides of the same coin, but it really depends on the system of reference, what we kind of experience, and what this body experience in terms of force. So real force is centripetal force, which keeps the body on circular trajectory and doesn't allow it just to fly away along some straight line. And apparent force is when this object, which is going along circular trajectory, experience some apparent force pushing it away from the center. So that is the difference between centripetal and centrifugal forces. And once we introduce the key parameters of this uniform circular motion, we can proceed further and try to quantify. So we want to know now not only the fact that there is some centripetal acceleration because of change of velocity vector orientation, but we want to know exact magnitude of this centripetal acceleration. And there are, as I mentioned at the beginning, two options, quite commonly, two approaches quite commonly used in order to do this. So we start first from a graphical representation, which is kind of a bit more easy to follow, I believe, but depends for who is quite good in calculus. That will be also quite simple to do analytical derivation, which we definitely go through also. So let us have another figure here because we want to make it not overcrowded. So let's consider again a circular trajectory. And here we have the center of this trajectory. Oops. Our initial radius vector, our final radius vector. So now we can draw one more vector which connects initial and final point of this object along circular trajectory. How do we call this vector? I mentioned several times previously. Displacement vector. You're right. So we have some paths. Keep your eye on this. That's important. So we have some paths which lands on this circular trajectory, and we have displacement vector. So focus your attention that the magnitude of displacement vector is smaller than the path, because this is a straight line, so this is a curvature. So we definitely want to remember that they are different, but we will come back to this a bit later. Bless you. So in order to move from point A to point B, this radius vector, it doesn't change in magnitude because it's circular trajectory, should be kind of tilted by angle theta. So that is the angle, let's call it maybe, I don't know, delta theta. So now we probably want also to have our linear velocity vectors. So this is initial and this is final linear velocity vectors. Remind you that this is right angle between radius vector and linear velocity vector. So now we can write that delta r vector, which is displacement vector, is difference between initial radius vector and final radius vector. Similar, we can draw for change of linear velocity vector. So let's show it here. We have initial linear velocity vector, then we have final linear velocity vector. Since linear velocity vector is always perpendicular to the radius vector, the angle here will be also delta theta. And the change of velocity vector as the difference of initial, like minus final linear velocity vector, will be delta v vector. So now we have two triangulars, and here we have the same angle. So we have so-called similar triangulars, and for similar triangulars, if we pick up the same two sides of the triangular, for instance, we consider this side and this initial velocity vector. Then we consider this side for second vector, second triangular displacement vector and initial radius vector. So the ratio between these sides for both triangulars will be the same. It will be equal because these triangulars are similar. So with this in mind, we can write that magnitude of this delta v vector, change of the magnitude of the change of linear velocity vector divided by linear velocity, just not vector, we just consider magnitude. That should be equal to the magnitude of the displacement vector divided by radius of the circular trajectory, because that is magnitude of the radius vector, and that is just radius of the trajectory, because it goes from the center of the trajectory towards the position of our body, and that position is always on the circle with the center which we define. So with this, we can express change of velocity vector. So let us do it here. Delta v vector, like magnitude of this change, will be equal to v linear velocity divided by radius of the curvature times magnitude of the displacement vector. So now we remember the definition of acceleration. Let us consider first some average acceleration. That is the ratio between change in velocity to the change in time. So shows how fast we change velocity over time. So we can write that acceleration average is equal to delta r sorry, that's about velocity, delta r, about acceleration, delta v vector over delta t. So when we have this, we can substitute in the numerator expression for delta v vector, which is this one. So we have the following: velocity, linear velocity vector divided by radius of the curvature times change magnitude of displacement vector divided by delta t. So now, as we usually do, let us assume that delta t is approaching to 0. So what we have here, if delta t approaches to 0, so means this time interval between two positions which we consider approaches to 0, then this object didn't have much time to move far. Means that this angle delta theta should also approach to 0, and final position vector should approach initial position vector. There will be a very small difference between final and initial position vectors, like radius vectors, but it will be very small. And in this case, the difference between, which I highlight, between the path and the magnitude of the displacement vector will be negligible, because they will be so close that the length of this trajectory will be negligibly small in comparison to the radius of the circular trajectory. And in this case, we can neglect the difference between path and displacement vector. So that means that we can express linear velocity vector as follows. So here we have this ratio delta, like change of change of displacement, change of position vector, which is displacement vector, divided by delta t. And this can be considered as linear velocity, because when delta t approaches to 0, the difference between path and magnitude of displacement vector becomes negligible. So in that case, we can write for instantaneous acceleration already, which we call centripetal acceleration, that it will be equal to v squared divided by r. So that is the magnitude of centripetal acceleration, which originates from the change of orientation of linear velocity vector. So magnitude remains constant, but orientation changes, and this orientation causes the centripetal acceleration. Also, if we take a closer look on this triangular with initial and final linear velocity vectors, when delta t approaches to 0, delta theta also approaches to 0, and final velocity, linear velocity vector, will be very close to initial linear velocity vector. So the difference, the change of linear velocity vector will be oriented, it will be very small, but its orientation will be almost perpendicular. The closer we come to initial velocity vector, the smaller is time interval in this angle delta t. The closer this delta v will be to perpendicular orientation with respect to initial velocity vector. So taking this into account, we also can make a suggestion about orientation of centripetal acceleration. So it will be, here we have our initial velocity vector. If change of linear velocity vector will be perpendicular to initial linear vector, velocity vector, then this orientation will be along radius vector r initial, which is always perpendicular to linear velocity vector, and it will be pointed towards the center. However, this is kind of assumption based on a limit for our triangulars, which we consider, and it's quite empirical approach for deriving analytical expression and finding the orientation of this centripetal acceleration. So the way how we can do it analytically is involving two additional parameters, which we will introduce right now. So let us first consider period and angular velocity. So do you know what's period? What in terms of uniform circular motion, how could you define the period? So it's time when which it takes for the body to make a full circle around its axis, which goes through the center of this circular trajectory. So in that case, how we quantify it? So it should be length of this trajectory, so means circumference of the circle, which is given as 2 pi times r radius, divided by linear velocity vector. Because we want to know the time, we divide path by linear velocity vector, and that is valid because we consider uniform circular motion. Linear velocity vector doesn't change in magnitude, so it only changes in orientation. So we can write here that period, which denoted is as capital T, is equal to 2 pi times r divided by v, linear velocity. So from here, we can express linear velocity will be v is equal to 2 pi times r divided by period t. And here, if we consider this term, 2 pi divided by t, so that is omega 2 pi divided by t. That is angular velocity. So we can write here that linear velocity is equal to angular velocity times radius. Keep in mind that angular velocity is measured in like units for angular velocity is radians per second. So 1 radian, 2 pi radians, that will be equal to 360 degrees. Means we have whole circle. So taking this into account, we already have expression for magnitude of centripetal acceleration, which is linear velocity squared divided by radius. So we can also express it in terms of angular velocity. So that will be for centripetal acceleration as omega squared times r squared divided by r. And that is equal to omega squared times r. And that is magnitude. We have nothing in terms of quantitative way of clarification about its orientation. We only know magnitude. So having introduced these parameters, in particular angular velocity, we can proceed further and start discuss our system which we want to use for analytical solution of this analytical derivation of the equation which describes centripetal acceleration vector as a function of time. So now we consider such a system. So will be system of coordinates with x and y axis. Here we have this circle, more or less circle. Here is our radius vector. Just r vector. Here is our linear velocity vector. They are perpendicular to each other. So now the question is how we quantify the position vector or radius vector r. We want to do some mathematical operations with a vector. We have this system of coordinate x and y, and we want to represent it in the form which is convenient for some mathematical operation. We discussed this already several times. Any suggestions? Maybe we recall our old good friends, unit vectors, I and j, which are oriented along axis x and y. We split our vector in two parts. Sorry. We split our position vector in two components and represent it as a sum of two components. One component will be projection of radius vector r on axis x times j unit vector, and another component will be projection on axis y times so was I unit vector, and that will be j unit vector. So let us do it now. And also, of course, we need to keep in mind that magnitude of linear velocity vector remains constant. It's uniform circular motion. So projection on axis x, it will be Rx, will be equal. So here we can show some angle theta. So it will be equal to R times cosinus theta, and Ry will be R times sinus theta. So with this, we can write now the expression for our radius vector. So radius vector is equal to R times cosinus theta times I unit vector plus R times sinus theta times j unit vector. We can take out of parentheses this R, the length of actually the radius of this circle, and that will be cosinus theta times I unit vector plus sinus theta times j unit vector. Okay, so we made a first step in order to represent this radius vector. However, this is representation of radius vector at some given moment of time. So it's kind of a screenshot of this motion. We have this given position of our body, and this radius vector gives this position in a given moment of time. We want to represent this radius vector as a function of time. So now, any suggestions how we are going to do this? Angular velocity. So what exactly we are doing with angular velocity? So look here, which parameters can change over time here in this equation. Radius is constant because this is our circle. So here is angle θ. So how we represent angle theta as a function of time? We can take a look on these units for angular velocity. It's radius, actually angle, divided by second. So it means we need to multiply omega, like angular velocity, by time in order to get radius. Here in the denominator, and then it will give us angle. So that means that theta as a function of time can be represented as omega times t. And since linear velocity vector is constant, omega is also constant. So now, when we substitute instead of theta omega t, we have not just one radius vector at given moment of time, but a time dependence of radius vector. So that will be radius vector as a function of time equal to radius r times cosinus omega times t times I unit vector plus sinus omega times t times j unit vector. So that's what we actually wanted. Now when we have this time dependence of radius vector, we need to take two derivatives because we know that acceleration is equal to second derivative of radius vector over time. So we need to take two derivatives. So first of all, we recall that omega is a constant. It's not a function of time. And second, we can recall here what will be the derivatives of cosine and sine. So derivative of cosine theta, that is minus sinus theta. Then derivative of sinus theta should be just cosine theta. Okay, with this in mind, we can step by step take two derivatives of this radius vector as a function of time. So first derivative, dr over dt. So what do we have? We have this constant untouched radius. Then we have minus sinus omega t. And we have another function in the argument of sinus. So we need to multiply first like derivative of cosinus by derivative of the argument of this cosinus. So that will be omega times I unit vector. So then we have another term with sinus, and that will be cosinus omega t times omega times j unit vector. So that's our first derivative. And we need to go further and get the second derivative, d squared r over as a function of t over dt will be again constant is untouched. Here we stay with minus because derivative of sinus will be cosinus. Will be cosinus omega t, and then again we multiply by derivative of omega t, which will be here omega squared times I unit vector plus, or actually not plus, yes, it will be minus sinus omega t times omega squared times j unit vector. So we are done with our derivatives. Now let us rearrange these things a bit. So that will be minus omega squared we can take out from the parentheses. So it will be minus omega squared times r. And here will be cosinus omega t times I unit vector plus sinus omega t times j unit vector. So now let us look at this result and what is this? Any suggestions? This part. Acceleration is everything. Yeah, but specifically this part. R times this parenthesis. So first function then. That is the same what we defined at the beginning. Since our radius vector is a function of time. Radius times cosine omega t times r unit vector, sinus omega t times j unit vector. If you look here, actually this is the same as this. So we can write here that it's equal to minus omega square times r radius vector as a function of time. So eventually we can write that centripetal acceleration vector as a function of time is equal to minus omega square times r radius vector as a function of time. So now what do we have here? First of all, in terms of magnitude, centripetal acceleration is equal to omega square times r. So this is the same equation as we got previously. We can take a look here. Yeah, based on our previously derived equation, v squared divided by r, centripetal acceleration magnitude is omega squared times r. So that is in terms of magnitude. And we come back here. What about orientation? Does it provide us information about orientation of acceleration, centripetal acceleration vector? So what do we have here? This is some scalar number. It's not a vector. So our centripetal acceleration vector orientation will be defined by orientation of this guy, of radius vector.
So it's opposite.
Exactly, because we have, in addition, on top of that, minus. So that means that by definition, position vector or radius vector in this case, if we have some circular trajectory, is pointed from the center of the trajectory towards the position of the body on this trajectory. So that is our radius vector. At the same time, we see from this equation that orientation of acceleration, centripetal acceleration vector, will be the same as this vector will be parallel to the radius vector, but oriented in the opposite direction. So it will be always oriented. Let me change the color. It will be like this. So this is our centripetal acceleration vector. So this equation gives us both magnitude and orientation of centripetal acceleration vector in very in the accurate form as a result of analytical derivation when we introduce this concept of angular velocity and represented the radius vector as a function of time with the help of this constant angular velocity. So let us summarize our discussion for today. So we had a chance to introduce the concept of uniform circular motion, which means that we have uniform or constant linear velocity. It doesn't change over time in terms of its magnitude. However, it changes in orientation. The change of orientation of this linear velocity vector results in so-called centripetal acceleration, which is always perpendicular to linear velocity vector and pointed towards the center of the curvature of this trajectory. With introducing this centripetal acceleration, we also mentioned shortly about the difference between centripetal and centrifugal forces, just to have it highlighted and clarified at this point. And further, we quantified centripetal acceleration in terms of its magnitude and orientation, initially with some graphical approach, which could be a bit easier to follow because of graphical representation. However, it gives us magnitude and based on some assumptions for triangulars, we can also estimate the orientation, but we don't get an analytical solution. So in order to get analytical equation for centripetal acceleration, we introduced two parameters for circular motion, which is period and angular velocity. So units for angular velocity is radians per second. With the help of angular velocity, we could represent the the time dependence of radius vector for uniform circular motion, and by taking two derivatives of this time dependent position vector or radius vector, we could get the final equation for centripetal acceleration, which gives us the magnitude and orientation in analytical way. So with this, we wrap up our discussion of motion in two-dimensional space and actually of kinematics. We will proceed further with already introduction of dynamics next time. And keep in mind, please, that we actually meet quite soon, tomorrow, because we study tomorrow for Monday. On Monday, our lecture is scheduled in the same time as today. We meet tomorrow at the same time as it's scheduled on Monday. So thank you very much for your attention and see you tomorrow.